Okay, I'm going to find the derivative of d of t. So d prime of t is, derivative of 13 is 0. What's the derivative of cosine? Derivative of cosine is negative sine. So I'm going to make this a positive 2.7 sine of exactly the same quantity, right? Pi over 4t. And then what else am I missing? What do I need to do?
Plug in the
D over dx, derivative of cosine u is negative sine of u times what? U prime. So what's u prime? The derivative of, in parentheses. What's the derivative? It's pi over 4. Yeah. So it's times pi over 4. So, I mean, you could put those numbers together, like 2.7 times pi over 4, whatever, times the sine of pi over 4t. But all I want is d prime of 3, because from 6 to 9, it's t hours after 6 a.m. T is 3. So I'm going to find d prime of t. So you pop it in, 2.7 pi over 4 times the sine of pi over 4 times 3. So type it in. Let's see what we get. What mode should I be in my calculator? Degrees or radians? It's in radians. There's no degree symbol, right? So pop your calculator in degrees. I mean, radians. Radians. And you're going to do 2.7 times pi over 4. This thing is really slow. Times the sine of pi over 4 times 3 in parentheses there. And you'll get 1.499. 1.499. What? You can't see anything? Uh-oh. Do you need to move up? So d prime of 3. Oh, sorry, I should have. What are we confused? What part are we confused on?
The 2.7 times pi over 4. Why is that? There's no t there.
So
I
it's just multiplying 2.7 times pi over 4. So because I had that at the end here, and I just moved all my numbers together because pi over 4 is just a number. It's a decimal. Okay. So I get 1.499. Okay, ladies and gentlemen, what are my units for the derivative? Hours. It's going to be remember, a derivative is a what of change? It is a rate. Yeah. Rate of change. So a rate is not just one unit. It's something per something.
Depth of the water over hours.
Depth of the, yeah. So it's feet per hour. Depth over, right? Ladies and gents, remember the derivative is the slope of the tangent line. What are units for slope? Y over X, right? Those are the units for derivative, Y over X. Your units of Y over the units of X. So the function d of t is in depth, which is feet. So that's feet over t is hours. That's like your X. Okay. So how would I interpret that then? What would you say? Anybody want to give me their sentence? Yes, no, maybe so. After 3 hours, what happens?
Increase at a rate of
Yep, depth.
1.99.
Yeah. Here's what I said. The depth will increase at a rate of 1.499 feet per hour. Just ignore that second part there. You don't need that for 2. Okay. All right. So here's what we're going to do. You're going to have about 10 minutes to finish up 2.2 worksheet 3. Most people only had 1 station left. So if you don't finish it in class today, you must finish that for homework. Does that make sense? Yes. All right. If you were absent Friday, the posters are still hanging around the room if you need to look at those for station 2. That will make it a little bit easier. So I suggest you do that for after Friday. Go ahead, 10 minutes. then I have to start a lesson.
Wait. Just like that, what's this new packet for? That for when
We're gonna start that today, and we're gonna start the new packet today.
after the-
Yep. Yeah. All right, go ahead and get your applications, position, velocity, and acceleration packets out. Okay. I also love, if you flip to the picture, I also love this picture. Not just the one in the beginning of your packet, but when you thought physics was science, but calculus is involved. So how many of you have had physics already? Or currently have it? Yeah.
Don't
So
take-
do you know how there's like so many formulas to memorize? I remember taking calculus. I took calculus after physics, and I was so mad because all the formulas I had to memorize, like the position formula and the velocity and acceleration, I had to do a simple derivative. You do a simple derivative to get them, and I was like, I didn't have to memorize these. Like I could have just derived them. Like anyway, so you'll find that out today. So calculus meets physics. Here we go. We're going to talk about position function, velocity function, and acceleration function, and how they're all related. But I have some, like, we got to go through some facts before we actually do some problems. So, couple facts. In calculus, all the motion we're going to do is called rectilinear. Rectilinear. Let me just tell you how many times. It's called rectilinear, which it's only happening along a straight horizontal or vertical path. Okay. So you're either going to have falling objects or traveling left and right, whatever. Velocity is the speed of something given a direction. In physics, we'd call that like a vector, right? So there is a difference between velocity and speed. Did you guys know velocity can be negative? Right?
Yeah.
It tells you direction, if it's going down or to the left. So speed, though, is the absolute value of velocity, and it's always positive. Good old Lightning McQueen there. Okay. The acceleration is the change in velocity over time, and that will tell you if an object is actually speeding up or slowing down. Okay. Couple more things. And these are just facts on your paper. So we're just going to go through these. Here's the crux of the lesson today. If S of t represents a position function or a height, we use S of t to represent position. S prime of t, the derivative of t, is velocity. S prime of t is v of t. We use v of t to represent velocity. And then the derivative of velocity, f v prime of t, is acceleration. And we call that a of t, right? Isn't that cool? Duh. And then velocity can be negative. It just shows direction because it's a vector. When it's negative, it's moving down or left. And when it's positive, it's moving up or right. Okay, that makes sense? Couple more facts. When your velocity is 0, the object is momentarily stopped and changing direction. So it also, when it switches from positive to negative, that means the object is changing directions. Okay. This can also be when the velocity is 0, when you have like a maximum or a minimum on your function as well. Okay. When the velocity and acceleration have different signs, then, I'm sorry, I'm on the same side. When they have the same signs, the object is speeding up. If they have different signs, it's slowing down. So really, acceleration doesn't tell us too much, except for when it's paired with velocity. It tells us, hey, the object is speeding up or the object is slowing down. Okay, so that's really all I'm kind of going to ask of you there. Okay, finally, we talked about speed already. So let's fill in the charts. Okay, so the position is a height or a distance. So that's going to be represented by the position function S of t. Okay, you might also see h of t, like, or h of t, like it's whatever they give to you, but typically it's S of t. That's the position. The distance, the units of a distance, you might see meters or feet or miles. Okay, whatever. Okay. Velocity. Velocity is the derivative of position. It's the rate of change of that. So we use, I want you to write this down. S prime of t is v of t. The derivative of position is velocity. And like I said, I'm going to have a song that helps you remember this. And then acceleration is the derivative of velocity. Now watch this. This is interesting. This is the first time, you guys know how you're excited about saying F double prime, right? So we're going to use S double prime. The double derivative, right? The derivative of velocity was the derivative of position. So S double prime of t equals, whoops, v prime of t, which is a of t. So the double derivative, the second derivative of position is the same as the derivative of velocity, which is acceleration. Okay? They're all connected. Yay, math is connected. So you take, we call it a higher order derivative, a second derivative. Okay? Distance over time squared. So like it's your like units you might see, meters per second or miles per hour or feet per second. Okay? Does that make sense? So those are your units. Oh, I'm sorry. I forgot to put units for velocity. That's for velocity. For velocity is meters per second, feet per second, or like miles per hour. Okay. Notice for acceleration, the units are over time squared. So that is meters per second squared, feet per second squared, or miles per hour squared. You have to square the time. It's like meters per second per second. So basically, because the acceleration is telling you about the velocity, it's meters per second for one more second. All right. You know how we use that phrase for one more second or one more hour or whatever. Okay. And that's the rate of change of the rate of change. Okay. So while velocity is rate of change of position, acceleration is the rate of change of velocity. All right. Then a key concept today, I know if you're still writing that, I'm just going to zoom out a little bit. The first, here's the key. The first derivative tells you how the original function is behaving. And that's the fill in the blank. And the second derivative tells you how the first derivative is changing, right? The first derivative tells you how the original f of x, right, is changing. And the second, whoops, lost my paper. And the second derivative tells you how the first derivative is changing. I feel like as I was working through these and refreshing myself on these problems, that helped me to make sense of everything. Okay. All right. Like I said, there's a lot of like setup before we get to the actual, let's do an example. So one thing you might be asked to find is average velocity versus, hey, find the exact velocity. The average velocity, remember, is slope. Whoops. What I want to do is slope. Okay. So the formula in physics for a position of a free falling object is 1/2 times the g, acceleration due to gravity, t squared plus v sub 0. You might also hear v naught. That is the initial velocity, right? That's in there. V sub 0 is initial velocity, what you start at, your speed you start at. It's 0 if you're at rest, right? Or if you throw something, that's the initial velocity, like where it started. And S sub 0 is the initial height of the object. So if you're dropping it from a given height, that's your initial height. All right. Okay. Initial position. Typically, if you're in, and here's like this, if you're in feet per second, the measurement is negative 4.9 feet per second, because it's, you guys know 9.81, negative 9.81 is like acceleration due to gravity times the 1/2 is negative 4.9. And then you guys remember meters per second? It's negative 32 feet per second squared. So times 1/2 is negative 16 meters per second. So when you see feet per second, it's always going to be negative 4.9. We just round there. And then for meters per second, it's always negative 16. Okay. For your leading coefficient for falling objects. All right. A visual, to visualize it. If I have a position function, which is a quadratic, it has a maximum height or minimum height. And then velocity Do you remember the derivative is the slope of this line? So the velocity is going to be the slope of that line at any given point. And acceleration, so if it's squared, the derivative of that is a linear, and then the derivative of a line is y equals something. It's a constant, all right? So because, I want you to notice something. Because acceleration is constant, a constant acceleration gives the velocity for the next second. It gives the velocity for the next second. Okay. So if you know that like your acceleration is 9.8 meters per second squared, our units here are meters per second squared, meters per second, and meters. If I add, or if I subtract 9.8 meters per second squared from the 18 minus 9.8 is 8.2. Do you see how it gives me the velocity on the velocity function for the next second, right?